Jump into the car on a Friday night, I wanna drive with you. Looking for a bar in the nearest town, I've never seen a sky so blue. We don't ever play it and the night is young, it doesn't matter what we do. There ain't nobody like, there ain't nobody like. You look so beautiful, and I'm so lucky to be yours. And you're taking me high. Ain't nobody like you, I'm not coming down. Ain't nobody like you. I could go 1,000 miles as long as I'm with you. Yeah, you're taking me high. Ain't nobody like you. Talking by yourself and you make me smile. I can listen all night long. I tell you about the time when I first met you, listening to our favorite song. Walking on the street when you caught my eyes, something about the way you move. No, there ain't nobody like, there ain't nobody like. So lucky to be yours. And you're taking me high. Ain't nobody like you, I'm not coming down. Ain't nobody like you. I could go 1,000 miles as long as I'm with you. Yeah, you're taking me high. Ain't nobody like you. 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 Jump into the car on a Friday night, I wanna drive with you. Looking for a bar in the nearest town, I've never seen a sky so blue. And you're taking me high. Ain't nobody like you, I'm not coming down. Ain't nobody like you. I could go 1,000 miles as long as I'm with you. Yeah, you're taking me high. Ain't nobody like you. Ain't nobody like you. Ain't nobody like you.
Stumbling out of bed, and I still got you in my head. From all those pretty words you said, it's like I'm wasted. Every time I see your face, I'm losing track of time and space. I don't know where I am, it's like I'm wasted. And I won't waste it. And I promise that I will stand by you forever. I can't get you out of my mind. I will follow you wherever. And I won't waste this. I'll follow you, yeah. I'll follow you, yeah. Could you come a little closer now? 'Cause I don't wanna slow this down. My heart is screaming out your name. I'm wasted on you. Here we are, right underneath the stars. So let's get a little reckless. You make me breathless, and I won't waste this. And I promise that I will stand by you forever. I can't get you out of my mind. I will follow you wherever. And I won't waste this. I'll follow you, yeah. promise that I will stand by you forever. And I won't waste this. I'll follow you, yeah. I'll follow you, yeah. I'll follow you, yeah. Yeah, I won't waste this.
Do you ever feel you don't get out what you're putting in? All your hopes and efforts are all in vain. Who will pick you up when you've lost everything? Does it all become for granted with a wedding ring? Oh, there must be more. There must be another way. There must be conscience. Different things in different ways. There must be love. There must be a reason. And a little bit of faith has got to come my way. I was just a little girl when my mama used to say, ooh, happiness requires work every day. Oh, and if that someone makes you smile and leaves you with a scar, don't let them tell you what you feel or who you are. Oh, there must be more. There must be another way. There must be conscience. Different things in different ways. There must be love. There must be a reason. And a little bit of faith has got to come my way. I gave it all to you for too There must be another way. There must be conscious. Different things in different ways. There must be more to the reason why we do it all for love. There must be more for a reason, and a little bit of faith has got to come my way. Has got to come my way.
Hey y'all, it's Jeff with Boots Flipped here, and we will have another night of electrical fun, I hope. So tonight, look at that, I grabbed the wrong collar. So tonight we are going to work with voltage drop. And if you've heard that word before, or you've kind of heard it thrown around, what voltage drop is it's what happens when we have a long run of wire, and we have whatever voltage we have on it at the time, but then we apply a load to it, and believe me, when we're talking about voltage drop, the biggest thing that we need to understand is it's the load that really causes the issues. So we'll talk about that in a little bit. But here's the thing. You need to understand it so that as you put together a system, that you can put together something that works well. And I want to grab this real quick. But let's look at the code. And why is it doing? There we go. All right. So if we look at the code book 21019A, branch circuits not more than 600 volts. Go to informational note 4, and conductors for branch circuits as defined in Article 100. Size to prevent a voltage drop exceeding 3% at the farthest outlet of power, heating and lighting loads or combination of such loads, and where the maximum total voltage drop on both feeders and branch circuits to the farthest outlet does not exceed 5%. Provide a reasonable efficiency of operation. So here's the thing. What this is basically telling you is a voltage drop of 3% over the circuit, a voltage drop of no more than 5% from where the power comes into the building to the farthest circuit would be acceptable, and it will provide, decent enough power for what you're doing. Now, this is in the code book, but remember, it's an informational fine note, or it's an informational note. I'm so used to, they used to be called fine print notes. Now they're informational notes. So it's not enforceable by the code, is what I'm trying to say. So it's in the code book, but it's just a note. And so what we're looking for, and what we're going to talk about tonight on branch circuits, is a voltage drop of no more than 3%. And let's go ahead and get into our voltage. Oh, come on. Our voltage drop. There we go. Our voltage drop and how we are going to do this. So, all right. So if we look at this formula, voltage drop equals 2 times K, and if you look down below, K is 12.9 for copper, 21.2 for aluminum. It's I is your ampacity, and L is your length over circular mils. With that formula, you'll be able to find your voltage drop over the run of a cable. Now, if you know what your voltage drop is going to be, then you can use the second formula, which will then tell you what size of cable that you will be able to run. And it's the same on the top. You're just dividing it by your total voltage drop. And then that will give you your circular mils. And then we will find what our circular mils are in a table in the code book. So I'm going to go to that real quick right now, just so you can see that. So in table 8, under conductor properties, I'm going to zoom this in, and we'll look at, let's just look at number 12 conductors. And if you look, there are 2 number 12 conductors shown. But then when you go over to quantity, that is actually the number of conductors or strands inside of that cable. So 1 would be a solid number 12, and then 7 would mean it was a stranded number 12. You need to move over, well, we'll talk about that in a second, but so 6530, if you look, 6530 is your circular mils for a number 12 copper. And that's the number that we need to understand. All right, so I also want to look at, if we look at the number 12 and we move over, and we'll look at uncoded And then we'll look at ohms per ohms per 1,000 foot. That's what K foot means. Make sure I'm in the right one here. So ohms per 1,000 feet is 2.01. Just I want you to keep that in mind. All right, 2.01. All right, so let's get back to here. So why this is important is you'll find a lot of times on a drawing, it will say that a drawing, a print will tell you that you have, like if you run a circuit over 100 feet, like a number 12 circuit, then they want you to run number 10s. And if you look at, if you run a number 10 circuit over 100 feet, they won't want you to run number 8s. And that is all because of voltage drop. And so let's take a look at that here just really quick so we can kind of see why that is what it is. So if I take my voltage drop and I have 2 times 12.9 because I'm going to be using copper. And then if we look at a number 12 circuit, using the 80% rule, 80% of 20 amps would be 16. So the maximum ampacity it could have on that circuit is 16. And let's take it times the length of 100 feet. Let's divide it by 6530, which was the circular mill area of a number 12. Let me grab my trusty calculator here. So if I take 2 times 12.9 times 16 times 100, that equals 41. Let's make sure I got that right. All right. And then we put that over 6530. And that equals 6.3 volts. All right, so that answer came up to our voltage drop for a number 12 going 100 feet with 16 amps on it is 6.3 volts. Well, if we look at our allowable voltage drop, so allowable voltage drop would be, if we have a 120 volt circuit times 0.03 or 3%, would be 3.6 volts. So if you look at that, if you have a number 12 that goes 100 feet, pulling the maximum amount of ampacity on it, the voltage drop would actually be too high, according to code, for it to be really reliable. So we would have to upsize that wire if we want to get that our voltage drop down. All right, so let's look at a number 10 in that situation. So to look at a number 10, we're going to go to let's go back to our table, and we'll look at a number 10. And a number 10 is 10,380 circular mills. All right, so if we take that same 41,280, it was 10,800. Let me make sure I read that right. Or 10,380, I'm sorry. And we divide that out. Give me a second. .97 volts. All right, so in that case, we're just a tiny bit higher than our allowable. However, that's close enough. I mean, we're just a little bit over 3% with that. So what this is telling me is if you ran a 16 amp load, 100 feet, number 10 wire would be the largest size that you would use. So where this becomes really important is anytime you're running 120 volt feeds to anything a long distance. And where I've run across this, and I didn't, as an apprentice, I never really thought about this, but a friend of mine had like an outbuilding that he put on his property, and he just wanted a circuit out there that was just to turn on some lights, have an outlet out there so he could plug something in. And he was probably, I don't know, about 150 feet away from his house. And we ran some just 120 volts, number 12, underground wire all the way out to that shed and hooked it up. And yeah, things came on and things worked. We didn't have, a 16 amp load. I mean, when we were looking at it, we did have, it would have been quite a bit less actually, but we had, sorry, I'm trying to erase my iPad here real quick. But when we did that, I never thought about anything. And here's the thing. The biggest deal is you think about voltage drop and you think about this long run of wire, and the first thing you do is you plug your tester in, like you just take a standard digital tester, and with that digital tester, you plug it in at the other end, and you got pretty close to the same volts you had wherever it was you tested in the house. And so you're thinking to yourself, well, wow, voltage, or there must not be hardly any voltage drop on this. We must be good. So let's just take a look at that for a second. So in that same case, if I had 2 times the 12.9 times, let's just say 1 ohm times 100 feet divided by 6530, that would come out to 2580 over 6530. And if we take 2580 divided by 6530, my voltage drop equals 0.4 volts. So if I put my meter out there, no big deal. I mean, to me, it looks like voltage is the same. We're good to go. Maybe it's a little bit less than what I tested somewhere else. And that's where it makes the biggest difference. And that's the thing you need to understand is it takes a load to cause the voltage drop. All right. So with my friend's house, let's see here. I'll try to erase this real quick. So let's look at what happened at my friend's house. So I had 2 times 12.9 times it, and let's say we had a light out there and it might have been 3 or 4 amps. And then I guess I put ohms in there. I meant to put amps before. 3 or 4 amps. And let's say, every once in a while he plugs, he's got some fluorescent lights in there. That's another 3 or 4 amps. So maybe he's at 8 amps times the length of 150 foot. So if we take that 2 times 12.9 times 8 amps times 150 feet, we get 30,960 divided by 6530. And that is a voltage drop of 4.74 volts. So now at that point, we're past our 3%. Now, if you think about it, if they had 120 volts at the house and you dropped it basically 5 volts, you'd be down to 115 volts. I mean, we see 110 to 120 all the time. So under that load in that condition, it would probably be okay. Unless you took, like a circular saw out there and you were trying to run it, you're going to probably end up having problems. So those are the things we don't think about because they are definitely the unknown. I had a situation come up on a project where they wanted to put some heat lamps inside of a small space, and we were 300 feet away or so, probably to the panel, probably closer to 400 feet. And I told them, we're going to have to use, I couldn't remember, I thought, number 8s, number 6s, something like that. And, they were like, don't overbuild this thing. It doesn't make any sense. Why do you want to do this? You're just trying to charge us more money. And in all honesty, it had nothing to do with trying to charge anybody any more money. But it had to do with this rule right here. And like I said, that's why it's important that you guys understand these things. So let's take a look at that real quick. So if I have 2 times 12.9, and when I'm calculating for something like that, just for the fact of the unknown, especially they wanted to plug in heat lamps, I figured, all right, so we're going to have 16 amps on there. And we're going to be 400 feet away. And my allowable voltage drop is, 120 times 0.03, which equals 3.6 volts, right? So I'm going to put 3.6 volts underneath here. And when we calculate this out, 2 times 12.9 times 16 times 400 is 165, 120 divided by 3.6. And that equals 45,866. So let's go over to our table. And when we start looking down our table, 45,866, start looking down your circular mill table and number 3s. So it's bigger than a number 4 because it's number 4 is 41,000 circular mills. So if you'd have to go up to a number 3. So if you were going to go 400 feet at 120 volts and you wanted to supply a 16 amp circuit, you would have to have number 3s to do that. And what is going on here? All right. Sorry. It was bothering me a little bit there. I knew I should be able to see more of this on my screen. So anyway, you'd have to have, I don't know what's going on there. So you'd have to have number 3s. All right, so we've used both of those formulas. So what happens then if we change something? So why don't we change our voltage? So there's a lot of times that you end up with parking lot lights, let's say, and it's not as big of issue these days because of all the LED lights, but that's not what I grew up on. It was always, like 400 watt or 1,000 watt metal halides, which took quite a bit of energy. And so when you started doing your voltage drop calculations for these circuits, in a parking lot, you could easily go, I don't know, 300 feet without really any problems. I mean, as far as, I guess I'm not saying without any problems, without even thinking, I guess you could easily get 300 feet of distance. And so if you're dealing with that, however, if we're dealing with it at 208 volts, let's see what difference that makes. So if I have two times 12.9, and let's say let's say for the sake of anything, let's just say we still have our 16 amps, and let's say we have our 400 feet, and our allowable voltage drop now, if we're 208 volt, that would equal 6.24 volts. All right, so let's take 2 times 12.9 times 16 times 400, and that is 120 divided by 6.24 volts. And that would equal, your circular mills for that would equal 26,461. So now if we go over to our table, and we let's see, let me get over here. There we go. We would be looking at, man, I don't know why that keeps doing that. Anyway, so we'd be looking at number 6 wires. Number 6 wires to go 400 feet to carry 16. Now, that is quite a bit bigger, obviously, than the number 12 wire or number 10, but it's not really that far out of line. And you'd see that quite a bit in parking lots. Now, here's the thing. If we did this same thing with 120 volts, and we did our 3.6 volts here, we did our 165, 120 divided by 3.6. Then our circular mills would equal 45,866. And we go back over here, and a 45,866. Now we're back up to that number 3. So we jumped up quite a bit, especially not only are you going to jump up quite a bit in conductor size, you're going to jump up quite a bit in pipe size. And depending on your pole base, you may not be able to get 2 or 3 pipes inside of your pole base that are the size that you would need for those conductors. So 208 would be a good thing. Now, let's take it one more step further. So let's say that we actually were doing 480 single phase on that times 0.03. And that would give us 14.4 volts So let's take that out. Put that in there. And we'd have 165, 120 divided by 14.4. And that circular mill area would equal 11,466. So once again, let's move over to our table. And now we are dealing with number 8 conductors. So a 16 amp circuit, we'd only have to bump up 2 sizes. We'd only have to bump up 2 sizes from what we would normally have with the number 12 with the 16 amps. And so that keeps us in a much better place, a much more easily installed place. And that's why you'll see anything that's run long distance, you'll see that that they'll do it with higher voltages for that same reason. Whoops, I did not want to do that. All right. So I want to do 2 more, but we're going to do it. I'll put it up on here, and then I'll give you a few minutes to kind of do it on your own, and then I'll come back and we'll do the answers. So let's do the first one, trying to find what our voltage drop would be. So if I had 2 times K, 2 times 12.9 times, let's say we're going to run like something big somewhere. Let's say 36 amps. And we're going to run it 120 feet. All right, so 36 amps is something that we'd run on 36 amps. We'd have to run a number 6 for. So the circular mill size of that is 26,240. All right, so I'll give you whoops, I guess you were just watching me that whole time. All right, so I'll give you that, and we'll just take a couple minutes and let you work that out.
I've been dreaming all night, bringing me some inspiration. Never meant to love no one, but baby, I saw you for a second and I'm happy that you came my way. Don't wanna waste no time without you ever brightening up my days. Never meant to fall so hard.
All right, so with that, with this calculation here, let's do it really quick. So 2 times 12.9 times 36 times 120, that equals 111 456 divided by 26,240. And that gives you voltage drop equals 4.24 volts. So if you're going to do 120 volts, that's the 3.6, right? Let's say you're at 240 volts. That's 7.2. And let's say you're at 480 volts. That's 14.4. So in this case, really, if you were running that 26240, if we go back to our table, the 26240 was a number 6 wire. So if you're running a number 6 wire, 120 feet, and there was a 36 amp load on that, you'd be pretty close at 120 volts. You'd be right on the edge, but you'd probably be okay. But if you're at 240 volts, you would very easily make that. And you can see definitely how it makes a difference as the voltage goes up. So why don't you go ahead and do this one? We'll do the same thing. And let's just solve. Let's just solve for the different voltage drops. Solve for the 3.6, solve for the 7.2, and solve for the 14.4. And so we already know that it's 1,1,1,4,5,6, right? So go ahead and solve for those, and then and we'll come back here in just a second. All right, so let's do these real quick. We'll do 111, 456. If we divide that by 3.6, so 3.6 voltage drop gets us a 3960. And if we go to our sheet, a 3960 would be we'd have to use a number 4. All right, so this equals a number 4. Now, if we went with 7.2 volts and we did our calculation, that's 15,480. And if we look at that, 15,480 would be a number 8. And technically, a number 8 would be technically too small for that circuit. But that's all you would need to carry that load at 240 volts. So let's look at 14.4 volts. And that's 7740. And if we look at that, we would have to have a number 10. And a number 10, you can only put 30 amps on that circuit. So you couldn't use a number 10 at 480 volts, but a number 10, once again, would be all that you would need to make that work. So one thing that I want to do real quick, just explain a couple things on here. So when you guys are looking at, you might say, okay, how come there's always a 2? Well, the 2 is for when you have your length. So when you go out 100 feet, you have to come back 100 feet to complete the circuit. So that's why the 2 is there. That K being 12.9 for copper, what that is that is ohms per circular mil foot. So I'm gonna see if I can. I was kind of playing around with this earlier, and that 12.9 is a it is an average of all the wire sizes. So if you take let's look at a number 12, and it is let's see here, number 12 solid uncoated is 1.93 ohms per 1,000 foot. So you would divide that by 1,000, and then you would go over to its circular mils, which is 6530. And you take that times 6530. Whoops, I pushed the wrong buttons on the calculator here. Hold on. 1.93 divided by 1,000 times 6530. 1.93 divided by 1,000 times 6530. All right, so that equals 12.6. So I'll do that on here real quick. So you have 1.93 divided by 1,000, and that equals 0.00193. Then you take that times the circular mil of the wire, 6530, and that equals 12.6. And what that is that comes out to be that is 12.6 ohms per circular mil foot. So if you think about it, a circular mil, there's 6,530 of those for a number 12 wire. So what you're doing is you're taking and you're looking at the ohms for a number 12 wire, which, like I said, was 0.00193, right? For 1 foot of number 12. All right. So that's, and then you take that ohms for that foot, and then you take it times the 6530, which is how many circular mils, and then you get 12.6. And if you think about it, the reason that number goes up is because you're dealing with a much smaller area, right? A lot, 6,530 times smaller than a number 12. And that's what you're actually getting. So you're getting 12.6 ohms per circular mil foot. Now we can actually look at a different one just to prove that, I guess, that this works. So let's go to a number 6. And if you look at a number 6, it's 0.491. So it's 0.491. And if we do that one real quick, .491 times 1,000. Oh, whoops, I'm sorry. 0.491 divided by 1,000 equals 0.000491. And then we'll take that. We'll take that times the circular mills, which is 26,240. And that equals 12.88. So, whoops, I guess I didn't do any of that on the screen for you. Sorry about that. So that would equal 12.88. So, like I said, they have went throughout that whole table and came up with a constant, basically, is what that is. So the 12.9 in there is actually a constant for copper, and it's just a number you can use. That's, you know, so they call it, they use K there. So you can actually, if you want to do an exact calculation, you could go and figure out exact K for that conductor if you wanted to, but that would be up to you. So anyway, I went longer than I'd actually planned to. I thought we'd only go about a half an hour tonight, and we've been about 40 minutes or so. And I appreciate you guys jumping on here tonight. Next week I will be back on Thursday at 7 again, and we will talk about. I haven't decided what we're going to talk about yet, so I'll try to post it on the in the comments on this video when I do that. So keep a lookout for that. I really appreciate you guys stopping by and checking this out. And, you know, as anything, as we move forward and kind of get in the groove of things just start to get better and better. And I'm really excited for that, because I can't wait to see where this thing really goes. And, you know, I think the chat part works. So if you do got questions or anything that you want to know when I'm talking, go ahead and put a question in the chat, and I'll try to go ahead and answer that right on the spot if it's possible. So anyway, once again, I appreciate you stopping by. My name is Jeff Boots. I'm here to just help everyone that's in the electrical field get better. That is my goal. So I will see you next Thursday. Thank you.